So now that you have some background in the point of the Laplace transform, the definition of the Laplace transform, and I introduced you to that table 6.2.1, part of which I've reproduced over here, I want to run through a problem from beginning to end where we use the Laplace transform to change the differential equation, or in this case, what we have is an initial value problem, because not only did I give you a differential equation, I also gave you initial values. And the Laplace transform changes it from a calculus problem to an algebra problem. So, as I said last week, step one, we're going to take the Laplace transform of both sides. We'll take the Laplace transform of the left side and the Laplace transform of the right side. So the Laplace transform of y double prime plus y equals the Laplace transform of 0. So the Laplace transform of the left side is the Laplace transform of y double prime plus the Laplace transform of y. What we have here is a linear function, so it breaks up over pluses and minuses. And the Laplace transform of 0 is just the function 0. So the Laplace transform of y double prime, now we want to take the Laplace transform of y double prime. We go back to rule 18, and we did this last time. We saw the Laplace transform of y double prime is s squared times the Laplace transform of y minus, now the s goes down in power by 1, so s squared, s to the 1, and we take lowercase y of 0 minus, now the power here goes down from 1 to 0, so s to the 0, we don't even write it, and the derivative goes up by 1, y prime of 0. So this, and I guess we could write s squared capital Y of s to indicate that the variable really is s. All of this is the Laplace transform of y double prime. Now the Laplace transform of y is just capital Y of s. That's just the definition. This is the Laplace transform of y. This is the Laplace transform of y. All of this together is the Laplace transform of y double prime. And that equals 0. Well, I don't know if it's clear to you because we still have a derivative here, but little y of 0 and little y prime of 0 and little y of 0, these are just numbers that we were given in the problem. Let's go ahead and put those in. S squared y of s minus s times y of 0. Y of 0 is just 1, so that's just 1 times s, minus y prime of 0, that's just 2, plus y of s equals 0. We just have an algebraic equation now. There's no derivatives. So let's go ahead and move everything without a capital Y in it to the right side. And what we're left with is s squared capital Y of s plus y of s equals, let's say, s plus 2. Over here I could factor out the y of s times s squared plus 1 equals s plus 2. Algebra, algebra, algebra. That's the only thing left. Divide both sides by s squared plus 1. So y of s is equal to s plus 2 all over s squared plus 1. Now what we want to do is massage this into a form where we can use our table to bring us back over to the right-hand side. I'm going to break this up into two fractions. I'm going to write this as s over s squared plus 1 plus 2 over s squared plus 1. Now that I see right there, where a is 1. So I can use that. This doesn't quite look like this yet, but it would if I pulled a 2 out in front. So s over s squared plus 1 plus 2 times 1 over s squared plus 1. Okay, so now this looks just like that, where a equals 1. So let me erase this part down to about here. Now we're going to take the inverse Laplace transform. So we've done all our algebra. Now we want to take the inverse Laplace transform of the left side, y of s, and of the right side. Again, we're going to take advantage of the fact that the Laplace transform and its inverse are linear. So it breaks up over the plus sign, just like a derivative does. And we can pull constants out. So I'll just leave this alone for a second. So what we do is we take the inverse Laplace transform of s over s squared plus 1. We can break it up over that plus sign, and we can pull the 2 out in front of the inverse Laplace transform. So all we did is we pulled the 2 through the inverse Laplace transform. Instead of sitting right in front of the fraction, we could pull it right through. You could do that with a Laplace transform or the inverse Laplace transform, because both the Laplace transform and the inverse Laplace transform are linear. And lastly, let's just go ahead and write our solution. So the inverse Laplace transform of f of s would be little f of t. The inverse Laplace transform of capital Y of s is just little y of t if you like. You can put the t of t in if you want. The inverse Laplace transform of this, let's just walk over here. We see that right there. A is equal to 1. This is cos t. Plus 2 times the inverse Laplace transform of that. Here we have this expression, looks just like this, where a equals 1. Sine t. Done. And again, if you want to put y of t in here, that's fine. We solved the initial value problem, this differential equation, with these 2 initial conditions, and there it is.